Thank you, and welcome to week 3 of the Bioinformatics and Genomics workshop series. Today, we're going to be focusing on sequence manipulation, alignment, and a little bit of assessment. I would like to apologize for last week being incredibly theory heavy. And what we're going to be doing today is that we're going to use some of these tools and see how I approach using some of these tools for my own research. So my coworker Jeff has posted in the chat regarding today's materials, or let me check properly. Jeff has posted the general wiki, and if you were to scroll down to the workshop program, please look over here, 917, where we do look at some of the tools. I would like to apologize also because I did forget to update the description over here, but nonetheless, the materials are right there. So if you were to click this little link over here, it's going to open what we're going to talk about today, an introduction to building a transcriptomics pipeline, RNA-seq alignment, and analysis. Now, before starting, it is extremely important for people to know that there is so many ways we can get about this. In this image that I have put right here, Griffith's lab runs a workshop series very similar to this. What is that? Oh, thank you, Jeff. A workshop series very similar to this, which focuses on some of the tools that you see over here, such as HiSet2, string tie, and ball gown. Today, we are not going to be covering string tie and ball gown, but we're going to be looking at using feature counts and DSEC2 on top of a couple of tools that we used last week, such as HiSet2, the aligner, and SemTools, the tool that allows us to modify some of the alignments within our compressed files. The schedule for today is we're going to be talking about alignment and data preparation for the next 20-ish minutes. We're going to be looking at transcript assembly and quantification, and then we're going to be doing some exploratory differential gene expressions. I see that you guys have your computer, so good, because Haley has already done it. Haley has already started the Bioscience app on Cybers. Otherwise, that is the next step that we need to do, starting the Bioscience app on Cybers. And how do you do that? Alrighty, I'm going to show you. I'm going to go to Cybers, so de.cybers.org, and write, I expect people know at this point how to log in already. Right here at the top, look for Bioscience. And within the apps, it should come up as Jupyter Lab Bioscience. Let me make this a little bit smaller so that I can actually see my screen. I'm going to copy this and paste it into the chat for anybody that has difficulties finding it. Please do open it. And within the launch page, click Next. And here, last week, I asked you to start with 8 cores. This week, we're going to do 16. So we're going to do 16 minimum CPU cores, 16 minimum memory, and 16 maximum memory. So 16, 16, 16, 16, 16, 0, and 16. It has to be said that all of this is already present in the notes themselves. So if you can't follow along for some reason today, go ahead and read in the notes. All of this is there. Once you are at this page, just click launch. I have already started one, so I'm not going to go ahead and launch one. But it should take maybe a minute to have one running. I'm going to go to one that I have just launched right now. Okay, so before getting into the themes of the day, we need to get data. Data is important for today, and we need to do a couple of things to get the data. Gonna go back to today's lecture, and if I were to scroll down over here, we have the explanation of the data that we're going to be using. First of all the data that I'm going to be using today is essentially coming from a single paper, and that is the transcriptome RNA sequencing data for data set of differential gene expression in E. coli, wild type, and SLY mutant strains. Now, if you were to look at the publication itself, what this publication is essentially just an announcement of, hey, we did this. And what is this? Well, these are what we call SRA accessions. And if you were to click on, for example, one of these, it's going to take us to NCBI. NCBI is where all of the data is at. And it gives you all of the technical information for you to understand what this specific read, what the specific SRA sequence, thank you, what this specific sequence is made of. Now, I'm gonna close this as we're not gonna be talking too deep about the paper itself. I want to let you know that we are taking 4 SRA sessions from this paper. And these have already been processed in a way that the FASTQ file is ready for downstream processing. So if you were to look at the entire pipeline, the first couple of steps have already been done. However, these steps are now in Cypress, and I'm going to show you how to get them. And by the way, this is the pipeline. So we're going to do, ideally, the pipeline gets the SRAs from NCBI, converts them to FASTQ, aligns them with the HiSET2 aligner, converts them and sorts them with SAM tools, quantifies them with feature counts, and performs differential expression analysis with DSEQ2. All right, scrolling down, we have already done step number 1. We have already started our Jupyter lab. Now, let's go get our data. First things first, transfer tools. We use our in-house transfer tool called Go Command Init. I'm going to show you how to use it. Please go to your Jupyter lab, and it should look something like this, where here you go to the terminal here at the bottom. Click that, and you're gonna type in I'm not typing here. Go CMD. I'm gonna make this a little bit bigger. Init. Go CMD stands for Go Commands, and it stands for Initiate. Press Enter, and now it's going to ask iRODS host. What are you gonna do? You're gonna press Enter. iRODS port 1247. What you're gonna do? You're gonna press Enter. iRODS zone. What you're gonna do? You're gonna press Enter. And if it does say iRODS username, your username, you can press Enter. If it doesn't say your username, please put your Cyber's username. And when it says iRODS password, please type your Cyber's password. Do keep in mind that when you type passwords in Ubuntu environment, you do not see the characters being typed. So here right now, I'm typing my password. I'm gonna press Enter. And if it gives you back the command line, then all is good. If it gives you back an error, please do Go Command Init again, because something has gone wrong. Give you a second. Okay. So if we go back to the notes, so that I'm gonna type also in the chat the various commands that happen. First is go cmd_init. The second command is slightly longer, and I do not expect you to be typing all of it out, because it's the command to actually get and fetch the data from Cybers. I'm going to paste over here, and a little bit of syntax. Go command get -- progress. I like little lines that get filled over time, and the location of the files themselves. I'm now going to press enter. And if at any point things get stuck, stop it with Control-C and enter it again. Seems like things are going. Oh, it's this big output.sem. And we are done. Okay. Eric, just give me a second. I'll make sure that you have access. Or Eric, did you sign up to Cybers using your University of Arizona account? Because if you didn't, then you won't have access to it. If you... Oh, I see. Okay. I'm gonna go ask my friend Jeff to help me out here. Jeff, there is a person called Eric Prylson in the chat to please give him Vice access. Can you do that? Thank you. Hang in there, Eric. Jeff is gonna help you out. Okay. Excuse me here, a little bit lost my train of thought. But what have we done so far? We have gotten some data from Cybers, and I'm gonna go do the last step, which is cd change directory in the E. coli genomic folder. I'm gonna paste this in the chat. Notice how when I do this, I am inside the folder now, and I can do ls-lh to show me everything that is inside this folder. CD stands for change directory, and ls stands for list, long, and human, the various items that are in here. So what is in here? And I'm going to have to switch back because this is the list of files that is in here. One, there is the E. coli, excuse me, reference genome, which ends with an extension called FNA. There is the transcript annotation, which ends with an extension called GTF. There is a number of SRA files, or in this specific case, SRR files. They are nomenclature things in FASTQ format. And then there is a single compiled reads in SAM format called output.sam. Spoiler, we can create output.sam in the lecture today, but it takes 10 minutes. We don't have the time for it, so we just have to do with a pre-compiled one that I have created. It also comes with a Jupyter notebook, which has all of the commands that we are running today, and an R script, which has all of the DSEC2 code in order to create a small little graph and quantification. Now, fantastic. We are at a point where we have launched all of our Jupyter notebooks and we have the data necessary to do some science. Let's understand a little bit what is going to happen. The first thing that's going to happen today is that we have to align each of the sequence data onto our genome. So if you scroll up again, you're going to see that we do have the genomic reference genome, and the idea is to align each single read onto the genome. Ideally, what does this do? Well, ideally, once you do have a reference genome, I'm going to be using my water bottle here as an example. What I'm trying to do is that I have I just want to make sure, transcriptome file, and I want to make sure to understand where it stands on the genome itself. And we want to do this for every single file that we have. Now, usually this is something that happens with many more files. We only use 4 today, but 4 is good enough for an example. Now, the tools that we're going to be using are HiSet2 and the SAM tools. Okay, so first things, if you do recall from last week, HiSet2 requires the genome first to be indexed. This is the command that we are going to be using, and the syntax is over here. We need to run HiSet2-build, and then we show how many threads we're going to be using. We have a machine with 16 threads, so we use a -p16. Then we have to add the name we have to point it to our reference genome and give the name of the genome of the index. So I'm just going to copy this and paste it for everybody else. And I'm going to go back to our Jupyter lab. I'm going to click no over here and paste this over here. Notice I don't change anything. Everything should be able to run, and you guys should have the same result as I do. Also, do notice how many files there are before and after we run this. I'm going to press enter. It was really fast. It ended in roughly 1 second. So what did this do? It created, I'm going to do ls-lh again, a number of index files. What are the index files? Now, I don't want to get too deep into this, but the index files essentially tell HiSet2 where each of the features are. It blocks them off in this specific case in 8 different blocks of memory. And through these blocks of memory that have been filled with information, it creates an HT2 file, which is where the information of the index lives. Now, I'm not going to go back down that rabbit hole again. But what we need to know is that we have created an index file. Cool, fantastic. Let's move on. There is some extra flags that you might want to use in your own research, and these are --SS, standing for splice sites, if you know if there is in a reference genome, and also point out where the exon are. But now we have created our own index file. We want to go ahead and create a compiled SAM file. Now, how do you do that? By using HiSet2. HiSet2 is very powerful. And again, if you do recall from last week, it's really good for pair and reads, and also for this thing called splice sites, alternative splice sites. We do not have splice sites today, and we do not have pair and reads. We only have a single and read. So instead of doing -1 and -2, standing for going this way or going that way, we do a -u. So that's pretty straightforward. Why -u? I have no idea. And then we want to highlight the output with a -s. Why? Because that outputs a SAM file. -s stands for a SAM file. They try to really help us out with nomenclature here, but sometimes it just, damn, guys, pick better names. Whatevs. All right, so if you do recall from last week, in order to assemble multiple single read FASTQ files using the -u, you will use the comma in order to separate each file. Now, it is up to you whether you want to run this or not. I'm copying and pasting it into the chat, but forewarning, this runs for roughly 10 minutes. You're running it.
Nope, it didn't work.
It didn't work? What do you mean it didn't work? Okay, I'm gonna run it then.
No such file or directory. SRR1397, the FASTQ file, doesn't know where that is.
I'm gonna press enter here. And it's running for me. So I don't know what's wrong with yours. Are you in the right directory? Are you in E. coli genomic? You're still in the home folder. Okay, everybody. It's Jeff's fault. But okay, so I have ran it because Jeff challenged me to run it. So I'm running it, and this is gonna run for 10 minutes. But if you do not want to run it, we already have the output right here. It's a 3.8 gigabyte file called output.sam. Now, why you will want to run this and why you wouldn't. You wouldn't because you want to save time and and you want to because it gives you some quite interesting data. So I'm gonna wait for it to come out, but likely the output it's going to give me is similar to this, where 11,395,529 reads were found. And of these, 11,232,207 were aligned 0 times. Only 1.30% of the entire amount of reads we have aligned to the genome. This is extremely poor. 1.43% is probably one of the worst alignments you could ever create. But here's a question for people here, people online. Why do you think that is? Why do you think the alignment was poor? And overall, what can we do with this? Yes.
What's usually considered a good alignment? Like what range?
I like alignments that are above 90 to 93%. Anything above that, great. 95%, super great. 98%, that's 99% is God tier. 79 is something that I would not really think is good. In the paper, their alignment is 79%, which is, you know. Joel, yes, that's exactly it. We did not trim the reads. We did not prepare the alignments, the FASTQ alignments for these. Because I did some looking into, they do go ahead and trim the reads. They do using Trimomatic, which is a popular trimming tool. And they also use a different aligner, star aligner, which may be a little bit more useful for this specific sequencer. So there is a few things that we have not done, and that is something that it's worth exploring. 1.43% total alignment rate, bad. Just bad. What now? In your own time, not now, I have added here some an exercise for you to run, and it's essentially how you will get around with getting your own reads. You could get the reads from the paper that I have mentioned over here. You can try at trimming the ends, for example, and see if a lot of these reads align. You can also have more than 4 FASTQ files for you to use. And honestly, I suggest you try this out in your own time, simply because it's an exercise. And if you do want to do transcriptomics or differential analysis expression, this is something for you to keep in mind. So I'm going to go back to the round over here. It's still going. I'm going to stop it because it's going to take a little bit longer. And I am just going to download it again. Oop. You should not need to do this. How long were the reads on average? Did long reads not align because the accuracy of sequencing falls the long? Oh, excuse me a second. Did long reads not align because the accuracy of sequencing falls the longer the read, and the short reads were more accurate and they were able to match? These were short reads, so roughly, I need to go and see this. But these were roughly short reads. Going to go fetch the paper itself. Well, these were not as short as I remember looking into this. These are fairly long, actually. Randall, I think you're onto something here with the accuracy dropping after some time with the longer the read. I do, however, think that accuracy with longer reads should be more than the 79% mapped over here. Usually, if you're not using a nanopore and using PacBio, for example, you will get roughly 90 to 93%. And with nanopore, you get an average of 90 to 80 to 90%. Maybe the fact that these reads are so long through an Illumina machine, maybe that may be the reason why the mapping is at 79%. And yes, if these reads were shorter, this will be able to map a lot better. And that's why Joel earlier was saying you should trim the reads first. Thank you for the question, Randall. I'm going to go back to the Jupyter over here, which seems to be stuck. I'm just going to press yes over here. And this, if it gets stuck at 80.3%, I'm just going to restart it again. Oh, there we go. We are passed. Okay, now, ideally, you should go through the exercise of getting the reads from the various FASTQ files onto a single SAM file. But now, if you do remember, in your own alignment, all of these reads may be pointing in one direction or the other. They're not in the right direction. I was pointing at the camera, I'm sorry. So the next step over here, now I'm going to get back to here, is to, well, first of all, it's to deflate the amount of, it's to deflate the file itself. And that is by using SAMTools view in order to convert it from a SAM file to a BAM file. If you could recall last week, SAM files are human readable, which use a lot more words, and a BAM file is computer readable. Less words, more numbers, smaller file. So I'm just gonna copy this and paste it into the chat for y'all to run. I'm gonna go back to over here where I am also just going to paste it. I'm also just going to paste it and press enter. Shouldn't take long. What am I doing here whilst this runs? I'm calling SAMTools and SAMTools view specifically, and I'm asking with the @ sign the 16 threads. Now, because this is yet another tool with yet another syntax, the people that created SAMTools decided that the threads symbol is an @. Would you understand that? Would you know that? No, you wouldn't. You have to read the manual. I'm sorry, everybody. And you're saying $S as a incoming SAM file and a -B as an outgoing BAM file. And this is essentially what we're doing. We are taking a SAM file and we're converting it into a BAM file. If we were to do ls-lh, I would like to compare these two specifically. And all of a sudden, we are going from 3.8 gigabytes to 700 megabytes. When you are sparse for resources, when you are a laboratory that can't afford having an HPC, you very much want to use a BAM file here. You can delete the SAM file if you want. Just do not delete the raw reads. So in this specific case, we do not need to care about file sizes. So I'm not going to delete anything. And I'm going to go back over here where I am going to talk about the sorting. We are going to give some directionality between the poor reads that have added, the 1% the reads that have added. And this is another of the SAM tools commands. We're going to go back to using the @ at 16. We're going to use 16 cores. And here there's an extra one. And then it's the -m. -m stands for dash memory, where we are going to highlight 8 gigabytes. It's really important for you to add the G, because if you do not add the G, the computer thinks you're asking for 8 bytes. Good luck with that. So I'm just going to copy this, paste it in the chat, and also run it. Shouldn't take long to run at all. I'm just sorting the reads out. There isn't that many anyway. And it's done. There is absolutely no change from our side. The size is still the same, but the contents have changed. One way that you can view the contents is by using SAMtools view, but this is not something that we need to care about at the moment. Oh, my bad. Because in the beginning, I had a little bit of difficulty to understand why we need to do the sorting step and tell the reads where to go. It's more not only to give them directionality, but actually for the downstream tools to be able to find the read easily or more easily. For example, over here, we have an unsorted file with read 1 being on chromosome 1, read 2 being on chromosome 2, and read 3 being back on chromosome 1. After you sort this, all of a sudden you have read 1 on chromosome 1 and read 2 being moved from the third further away down table to a lot closer to read 1, which is where having them both on chromosome 1. So it allows for quicker processing downstreams. This is optional. We can index the genome, but we don't need to. We don't need to because the next tool, I was going to be using string-tie for this, and string-tie requires an index, but bioinformatics is funny, and sometimes things don't work. So we do not necessarily need to index our genome right now or our sorted reads right now. And to take a breath, I'm going to step back and show you what we have so far. We have a sorted output. Oh, it is slightly smaller too, 751 versus 768. We have a sorted BAM output, which we got by aligning these raw reads, which we did not trim, onto these reference genome. Going forward, there is a couple of files which we need. First, obviously, the reference genome, but also the genomic GTF, and we're going to go into understanding what GTF and GFF are right now, and the output sorted.bam. All right, break's over. Going back. The next step is we're going to be quantifying gene expression. We're going to, here is a little bit of an image. I try to find good images to kind of make you all understand what is going on over here. And when I do look for images, I always find other tutorials and I try to connect. I know that there has been people that have been messaging me regarding, hey, where can I find other tutorials? I'm trying to implement things from other tutorials, such as the Harvard-Chan Bioinformatics core. If you do want to know more about genetics and genomics and learn how to do all of it, the Harvard-Chan Bioinformatics core, such as the Griffiths lab that I showed earlier, are great places to learn how to do bioinformatics. So, important things. Before we do some differential analysis, I want you to understand that features come in two files. GFF, standing for General Feature Format. These have all of the genomic features in them. File is slightly larger. It does count anything that goes from an exon to anything that may look like an exon. And GTF, which stands for Gene Transfer Format, which only contains gene information. It's a lot more specific. It's very similar to GFF, but it's a lot more specific. And when you do work with transcriptomics, you want to use the GTF file. Why am I pointing this out? Because when you are gonna go to NCBI to download the files, it's gonna look like this. And you're gonna look, oh my God, what are all of these files? What does this mean? So the point is, if you're working with transcriptome, look for the extension GTF. You're working with assemblies, genomic assemblies, for example, you want to look for GFF. Now there is a lot more over here. We're not going to go into it. Also, FNA will be your friendly, neighborhood-friendly FASTA reference genome file. So now I'm going to close it. Okay, now that we do know what the difference between GFF and GTF, we're going to go down a little bit. We're going to be using a tool called feature counts. Feature counts is an extremely simple tool. It does what? It counts. Yes, how did you know? And we wanted for this specific workshop to count genes. We just want to count the genes that are present. We don't want to do something too out of the ordinary. And I have a bunch of more notes over here because it's important for you to know that bioinformatics is funny. There is different ways to get about things and get different data. The reason why we didn't index the genome the alignments right now is because we don't need to. But if you, for example, would like to use string tie and ball gown, you will need to then create an index file. It really comes to what is your end. There is 100 different tools for 100 different ends. And right now, we just need to count genes. So let's go and count genes. First things first, what is reference feature counts? Or sorry, how does feature counts work? Well, you give it a reference genome and you tell it what to count. Wow, so difficult. Let's go. There is different amount of flags that you might want to run. In this specific case, we want to run the -G gene ID, which will print out the gene ID for the genes that we find. And we are going to also run the ignore duplicates. We just want to find out, excuse me, we want to just run non-duplicate reads. Why? Well, honestly, I just wanted to run it with non-duplicate reads. Just gonna copy this and paste this into the chat in case you want to run. And I'm gonna go back over here to my Jupyter lab and paste it too. It's going to use 16 threads in this specific case with a -T. I gave it the -A genomic GTF annotation file. I'm telling it, hey, I want my output to be called counts.txt. Tell me the gene IDs, and use the output underscore sorted bum as a reference, not a reference, as a, yeah, as a reference, alignment reference. I press enter. It looks kind of pretty. It tells you a bunch of information. And it tells me that roughly 1,103 alignments were assigned, which is sort of what we saw earlier. It ran really quickly, and it found 121 features. Congratulations, everybody. This was a really quick feature count. That's all that matters for now. Don't worry about it. Now, oh yeah, you can use head to look inside a file, especially that just the head of the file. But I'll do head counts.txt, press enter, and it kind of looks like this. Yay, fantastic. It tells me what the gene ID is, what chromosome is it on, where the start finish is, the ending, and which strand. There is a lot of information here. A lot of information can be used by a lot of different tools. But we know that we want to use DSEC2. And we now need to format this in a way that DSEC2 can take it. What do we have to do? First of all, there is many ways to get around this. But what we need to do is actually to get rid of most of this data. We want to keep only the gene ID and essentially where it is, or how many times it shows up in each read. So I say it again here, always keep your data. If you're an R person, go ahead and use R, but I am a command line person and I will go ahead and use AWK. If you have never heard of AWK, good. You never need to know about AWK ever again. I'm gonna paste this, and what is this going to do is that it is going to essentially trim it out, most of it, and then only keep what we need. I have put a small little explanation on how this runs. It keeps the first line and it asks the computer to just keep 2 specific columns. So yay, let's go ahead and cut everything out. AWK is extremely powerful. Don't use it if you don't know what you're doing. Now, fantastic. We can go ahead and do the whole head thing again. Head. Clean counts. I'm going to press enter. That's exactly what we saw earlier. However, this is not yet where we need to be. There is one more step. We need output underscore sorted.bum to be sample1. Now, you can do this through Excel, you can do this through R, you can do this through Python. I am a Nano and Vim sort of person, so I encourage everybody now to type in NANO clean counts.txt. Nano is an ancient data editing tool for the command line. I'm gonna press enter, and I'm now in a page editor. I'm gonna go to the right where output sorted bum is at, and I'm just gonna go ahead and delete that. Right as I reach the end, I'm just going to add sample1. Oh, that's sample2. Dang it. Sample1. And no capitalization, no underscores, nothing. It just has to be sample1. To get out of here, that's the trick. You have to press Control X at the same time. It's going to ask you, save modified buffer. You are going to press Y. It's going to ask, file name to overwrite. You're going to press enter. And then it gives you back the machine. I'm going to type that in the chat. To exit, type or press X, Y to save buffer, enter to exit and save. Yay. Okay. So now we have a clean count. Gonna do, oh, wrong chat. Head clean counts, and that is exactly what we want to see. We want to see a sample one instead of the output sorted.bump file. Fantastic. We are now ready. We now have counted all of the features that we wanted, all of the genes that we wanted, and we're now ready to move on to DSEC2. We have 10 minutes. This is going to take exactly that much amount of time, and it's our time. What do we have to do now? Going back to our Jupyter Lab. Jupyter Lab has the ability to run R as well. Go over here with the plus. So please plus, it opens up a new launcher. And right here, it has R Studio. Click R Studio. Should open up R Studio in a new screen. Yay, it opened up R Studio in a new screen. Fantastic. Sorry, I have to move a bunch of Zoom things around. Now, if I hope this is not your first time using R. If this is your first time using R, R Studio is an IDE. R Studio is an IDE, which stands for
Integrated Development Environment.
Integrated Development Environment. Thank you, Jeff. I always forget it. It's our job to know these things, but I always forget it. And which means that it helps you run its own code, or its own language, which is R. To help you, I have already written everything, so y'all don't have to do anything. And please do navigate to the R file itself. Go to data store and E. coli genomic and dsec2_viz.r. This should prompt open a little window over here on the left, which essentially has has everything annotated, basically, where you can read exactly what happens. In this specific package, everything that we need is installed. If you're running this at home or on your own computer, you might have to go ahead and install a few of these packages yourselves. So what are we going to do? We're going to do two things. One, create a really, 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 really simple heat map. And two, we're going to count the most expressed genes in our alignment. So easy peasy, lemon squeezy. We're going to load a bunch of the libraries that we're going to need. And these are DSEC2, ggplot, and reshape. To run things directly from the R file itself, you can either highlight it and press Control Enter. And as you can see here on the left, something is happening. Or you can go here and just press the Run button. I simply prefer pressing Control Enter a bunch of times. And what are we doing so far? We're just loading a bunch of libraries. Cool, fantastic. Now, second thing that we're going to be doing is that we're going to read in our cleaned counts. You will need to change this specific path right here. And I believe we can get away with just type. Oh, no, wait. Oh, no. We're just typing in /clean counts.txt. If I press enter, oh, no, it can't find it. Never mind, y'all. I'm gonna press, let me give you the right, there we go. E_coli_genomic. If I were to press enter right now, yes, it's in. So paste this in the chat. There we go. Cool, fantastic. Things are in. It is up to you whether you want to do some exploratory data analysis through the tools or right here in R. You can look at the structure. Zoom is very much in the way right now. Go away, Zoom. Thank you. You can look at the structure, or you can look at the structure over here. You can do head, which does exactly what we just did. So you can do a bunch of things in R to look at the files before you actually do something with it. Now, I have to create a D6 data set object in order to count and create our matrix. I'm not going to go ahead and tell you exactly what's going on, but what we need to understand is that design has one column. We know that we have ones. We are going to be counting data and creating a small little data frame with the amount of columns that we have. This is pretty straightforward. Just gonna press enter. All genes have equal values for all samples. We'll not be able to perform differential analysis. I know, and I've lied to all of you, because all we need to do, like all I want to show you right now is kind of like the pipeline way to get things ready for right here. We're not really doing differential analysis today because we only have a single sample. We're gonna do that in 2 weeks, by the way. This is some information that's gonna come later. All right, so now we're gonna use estimated size factors in order to normalize and count the data itself. So I'm just gonna press, I'm gonna press Control Enter in line 24 and line 25. Control Enter again. Extra points for anybody that tells me what normalization in genomics is important.
Things in different sizes, so you need to like normalize to make the comparisons equal.
Perhaps. This is something that's not clear to me as well. But the thing is, I had looked it up yesterday. I forgot to put it in the notes. I will be able to answer to you after this. So we can actually go ahead and create the matrix now. Oh, sorry. I'm getting ahead of myself over here. Here we go. ggplot, create the matrix. And this is the crappiest little heat map ever. But hey, something exists. There is some genes inside those very bad alignment. 1.27% or 1.43, whatever it was, gave us a little bit of a result. What did it give us? Essentially that those alignments contain some genes. This is not so good. This is actually quite extremely bad. Why? Well, it tells me that I've essentially cut out a lot of the fat, trimmed out a lot of the fat, and this might not be some genes that are of relevance. These are just the genes that exist in those samples. But imagine yourself not having 4 samples. Imagine yourselves having 20 samples. Imagine yourselves having trimmed some of these samples, and imagine yourselves having gone through this whole process, and you'll probably see a different set of genes being highlighted. Now we can actually go ahead, calculate the average expressions, and create sorted genes and force R to tell us what these genes are. Oh, come on. So ultimately, I'm sorry I'm rushing ahead. I'm just a little bit out of time, but the R file is right there, and therefore you should be able to reproduce this in your own time with some annotations. Yay, the average expression of a specific gene is higher than the others. Is this the gene of interest for you? Well, maybe. Who knows? So y'all, thank you very much for today. This was an introduction to what it feels like to create an assembly, actually using the tools that we talked about last week, and use some real world data to do some really, really high level analysis. We are going to, before I let me send this out. Oh. What? Now you all know my super secret password. And I'm gonna paste this in the chat. Please do fill in the short feedback. It really is a lot for us, especially because it helps me understand whether I need to go faster or slower, or whether I need to choose to cover other things. DSEC2 and working with DSEC2 is going to come back next week. Sorry, in 3 weeks actually from today. Next week and the week after, we are going to be talking about Nextflow and SnakeMake, because you might have seen a lot of these pipelines have a ton of different tools. There is some scientists which decided we're gonna put things together and make things run faster and smart using pipeline management tools. So that's what I'm going to cover the next couple of weeks, SnakeMake and Nextflow. And then in 2 weeks, we come back with DSEC2, proper deep dive with, again, real world data. I think we're going to be using mouse instead of E. coli, just because it helps with the wow effect, maybe. That said, stay tuned. Why? Because going forward, we have arranged to have RNA-seq only workshops. These are going to happen in November. We haven't figured out a date yet. Do you have a date or a specific day, or like within a week, which you will not be able to attend? Okay, all right, okay, so no Tuesdays apart from right now. That works.
I'm pretty flexible.
Okay, cool. No, I don't see anybody in the chat complaining, so maybe we are just gonna run it over here. The thing is, it's going to be a couple of lessons, and these are gonna be a lot more of a deep dive than what we have done so far. A lot more. Yes, Oscar. A lot more than I can cover and what we will be covering in 3 weeks. And because there is been no Friday, okay, and because there has been such a high amount of people asking for transcriptomic analysis, we're gonna make this a proper thing next semester. So thank you for your attention today. Keep an eye out for announcements regarding potential RNA-seq workshops coming either the week after or not. Hi, Michele. Unfortunately, I missed the first session and would like to review those sessions. I found the link to previous sessions. Do you have a... Yes, we do have recordings. I'm sorry. I know that a lot of you are messaging me about recordings. We have them. I just have to get back and reply. Oscar, I will give you access. Yes. Okay. All right. Since y'all, okay, don't disappear. Don't disappear. I gotta go. UA Data Lab. Now, if you go to YouTube and type in UA Data Lab, this thing called U Arizona Data Lab comes up, and we have all of our recordings here.